Okay, so today I'm gonna go back a little bit, और मैंने अभी देखे इसलिए टॉपिक नहीं दिखाया, और वो I'm gonna just discuss with you कि अभी जो everything that we've been doing with the principle of work and energy वो आया कहाँ से था. You guys, I hope, remember कि we had started, how we got our principle of work and energy was that we started with our equation of motion. And we had noted that if we're looking at just the tangential component of velocity, tangential component of acceleration, then I have summation ft is equals to mat, or at I know is just equal to v dot, right? इसका magnitude. So इससे हमें ये अंदाज़ा था, and we knew कि for this at, the tangential acceleration is the same as the one that we've done for kinematics for our straight line motion. मतलब ये कि इस tangential acceleration के लिए हमारे पास वो सारे dv by dt और दूसरा क्या था at ds is equals to v dv apply करते हैं, right? You guys remember this? So because of this, what we had done was कि हमने इसके अंदर in our equation of motion we had substituted this third kinematic equation which relates acceleration to velocity and displacement, and then we had integrated the entire thing such that हमारे पास फिर आ गया था f dot ds का integral, and that's going to be equal to half mv squared का limits लगा के. That is, we had gotten our principle of work and energy. You all remember this, right? सोचा आप लोगों की कल की क्विज की थोड़ी रिवीजन ही करवा दूं. मतलब ये कि we had taken our equation of motion straight forward, वही हमारी पुरानी घिसी पिटी equation of motion, और उसके अंदर हमने एक अपनी acceleration related to velocity and displacement वाली kinematic equation को input करके integrate किया था, और उससे हमें we got this principle which related the forces, the displacements and the velocities directly together. Now if you notice here कि we can do something else along this procedure जो हमने last time भी किया था. And the second option that we haven't yet explored is that instead of inputting our third kinematic equation, why don't I input this one, the more familiar acceleration, velocity and time relationship into my equation of motion, and then integrate. That is, just as in the principle of work and energy we had managed to find a relationship between the forces, displacements and velocities, this time perhaps once we use this equation, ये वाली इसको देखें इसके अंदर क्या है, then we will be able to relate forces to the velocities and times. And this is indeed what we're going to be doing today, and we'll see shortly that this particular manipulation of the equation of motion leads us to the principle of impulse and momentum. Okay, so last time we've been looking at work and energy, and now today we're going to see how, again from the equation of motion, how we're going to get the principle of impulse and momentum. ठीक है जी. So as I've already said, why don't I input into my equation of motion the expression for acceleration in terms of velocity and time. ठीक है जी. पहले हमने वो velocity और displacement वाली की थी, इस दफ़ा मैं ये पहली वाली kinematic equation input करती हूँ. And then clearly this is an equation which has got the forces on the left hand side and then dv by dt on the right hand side. What I can do is I can separate my variables जैसे हम करते होते हैं, मतलब ये कि right hand side पे सिर्फ एक वेरिएबल का डिफरेंशियल रखें और लेफ्ट हैंड साइड पे दूसरे वाले को ले जाएं, then I can integrate the entire expression such that what does this become? Left hand side पे it's then an integration with respect to time, whereas on the right hand side I've got an integration with respect to velocity. Just the dv रह जाएगा. And of course, the mass does not depend on the velocity for classical Newtonian mechanics, which is the realm that we're talking about. So the mass just can be taken outside the integral, and all I'm left with on the right hand side is just the integral of dv going from, or apply कर देते हैं हम limits, okay, maybe time 31 जिस पे v1 है, and then going at a later time t2 we've got a velocity v2. So that if I integrate this, this is just m times v, or v if I input my limits, I just get this right hand side mv2 minus mv1. Now this is basically, this is an initial representation of the principle of linear impulse and momentum. और अभी मैं आपको इसमें identify करना शुरू करती हूँ कि कौन सा impulse है, कौन सा momentum है. अभी हम इस पर बात करते हैं. Please just I want to point out कि मैंने इसको इतना ही expand किया है. Why? Because ये जो left hand side है ना, इधर integral of force with respect to time है, और force is most certainly going to be a function of time. ठीक है, बहुत ही कम cases होंगे जिसमें वो it's just a constant. Otherwise, we have to just keep this integral as it is. ठीक है, or summation is outside, which means कि हर force, every external force that's acting on a particle or a system, for that we're gonna have to find its integral with respect to time. Okay, now let's start to identify what each of these things are. First, I just want to ask right here कि अभी से किसी को कोई confusion कि ये हमने how did we get to this expression right here? Any questions about that?
मैम
जी.
इंटीग्रल लेके समेशन लेके या समेशन लेके इंटीग्रल?
फिर से सॉरी.
इट डजंट मैटर.
समेशन ले के इंटेग्रल है या फिर इंटेग्रल ले के समेशन है? एक्चुअली इट डज मैटर. द वाई इट मैटर्स इज कि वी हैव टू बी केयरफुल कि वो जो हम इंटेग्रल कर रहे हैं ना, वो फोर्सेस के टाइम्स पे डिपेंड करता है और उनकी इंडिविजुअल लिमिट्स पे. बाय दैट व्हाट आई मीन इज, इमेजिन इफ अ पार्टिकल हैज़ मल्टीपल फोर्सेस एक्टिंग ऑन इट, श्योर, बट ये वाला फोर्स जो है इज एक्टिंग फ्रॉम लेट्स से T1 to T3, या चले सॉरी पहले T2 कर लेते हैं. वेरेज जो ये F1 थी, तो इसका तो ये इंटेग्रल हो गया. वेरेज एक और फोर्स थी जो किसी और टाइम के लिए एक्ट कर रही है, मे बी फ्रॉम T1 till T3, right? So that's why the summation cannot be brought just right in, because the limits may be different for each of the forces. But if the limits are the same, that is, if they're all acting for the same time duration, then the order does not matter. You can swap them around. Shurjeel, does that make sense?
Yes, ma'am.
ठीक है जी, thank you. Okay, so let's अगर किसी को कोई क्वेश्चन आए जहन में तो डू आस्क मी. अच्छा, अब आई वांट टू स्टार्ट टू पॉइंट आउट व्हाट द थिंग्स आर, लेकिन उससे पहले आई जस्ट रिमेंबर्ड कि मैं फिर से ये रीइटरेट कर दूं कि हम करते क्यों होते हैं हर दफ़ा कि हम इक्वेशन ऑफ मोशन के अंदर ये किनेमैटिक इक्वेशंस डाल क्यों रहे हैं. Why? Because as we saw for the principle of work and energy, it allows us to skip a step, basically. सेम एज हियर दिस क्योंकि हमने वो पहले ही स्टेप कर लिया ना, मतलब ये कि वो किनेमैटिक्स को हमने पहले ही काइनेटिक के अंदर डाल लिया, काइनेटिक्स के अंदर. सो इट अलाउज अस टू ईट अप अ स्टेप इन आवर एनालिसिस, बिकॉज अब हमें ये जो प्रिंसिपल यहाँ पे मिलने लगा है, जो मैं अभी आहिस्ता आहिस्ता एक्सपैंड कर रही हूँ जिसके ऊपर, दैट डायरेक्टली रिलेट्स फोर्सेस टू टाइम एंड वेलोसिटीज. ठीक है, वरना अगर आप ये डायरेक्ट प्रिंसिपल ना यूज़ करें तो फिर हमें क्या करना पड़ेगा, हमें पहले फोर्स से एक्सेलरेशन निकालनी पड़ेगी, फिर उस एक्सेलरेशन से वेलोसिटी निकालनी पड़ेगी या टाइम निकालना पड़ेगा, राइट? सो दैट्स जस्ट द पर्पस ऑफ दिस प्रिंसिपल ऑफ इम्पल्स एंड मोमेंटम, एंड दैट वाज आल्सो द पर्पस ऑफ वर्क एंड एनर्जी. ओके, so be mindful that that's why we're doing this basically. Okay, so now let's identify what these physical quantities are. I'm going to start with the right hand side because it's just much easier to elaborate on. So this right hand side, this product of mass times velocity m times v. Please notice this is a vector quantity because the velocity is a vector multiplied by a scalar. So this is known as linear momentum. Okay, mass times the velocity of a particle. Okay, or as I said, it is a vector क्योंकि वो वेक्टर को मल्टीप्लाई कर रहे हैं हम एक स्केलर से, और ऑब्वियसली फिर वो जो प्रोडक्ट होगा उसकी डायरेक्शन भी उसी वेलोसिटी की डायरेक्शन में होगी. सो दिस momentum vector, linear momentum vector, has the same direction as the velocity v. Secondly, उसकी हम units भी easily find कर सकते हैं, just the product of mass times velocity. So it's kg meter per second. Straightforward. Finally, let's start to bring in some conventions which people use. So often people use a symbol, just this L, to represent linear momentum. और अब again ये L इसलिए है because it's linear momentum. There's another type of momentum which we will talk about later on, and that's the angular momentum. Abhi for now, let's just, abhi we're talking about just the linear momentum and hence this L. Okay. इसकी एक एग्जाम्पल देखते हैं. सो मोमेंटम बेसिकली वो फिजिकल क्वांटिटी इज ट्राइंग टू रिप्रेजेंट, नाउ दिस माय साउंड ट्रिकी, लेकिन इट्स बेसिकली ट्राइंग टू रिप्रेजेंट द अमाउंट ऑफ मोशन समथिंग हैज़. ओके, और इसी वजह से ना इसमें मास भी है और उस चीज़ की वेलोसिटी भी है. सो इट्स सॉर्ट ऑफ लाइक अ कंबाइंड इफेक्ट ऑफ द मास एंड द वेलोसिटी. सो लाइक कि उस पूरी चीज़ का क्या sort of amount of moment or amount of motion है. ठीक है, अब इसके बारे में सोचने के लिए just have a think कि if we have something of a small mass such as a cycle or something with a large mass such as a train, and they're both moving with the same velocity, then we know that a large mass will have a larger momentum, right? Because it's the mass multiplied by the velocity. And this thing which has a larger momentum and has a large amount of motion is therefore more difficult to stop. Does that make sense? So it's sort of like inertia, but not quite. It's like physically it works in a similar way essentially. Okay, so it represents the amount of motion that something has, and hence is this mass times the velocity, right? Okay, so that's clear. What this right hand side is, and clearly if I'm using the symbol L to represent them, then this is going to be my L2 and this is going to be my L1. Please don't forget that it is a vector. Don't forget this, very important. Next, what about this thing on the left hand side? The integral of force with respect to time. Okay, so of course the topic is the principle of linear impulse and momentum. We've already covered momentum. Now this thing on the left hand side is the linear impulse of a force. Okay, now this is represented using I for impulse, and again it's the integral of a vector with respect to time. So जो हमारे पास वो आता है, the output of that is also going to be a vector. Or essentially it is measuring the total sort of क्या कहें, मतलब ज़ाहिर है it's not, मैं जिस तरह टाइम की बात efficiency में करना शुरू थी, it's not just enough to think about कि वो force एक चीज़ पे act कर रही हो, but it's also important to think about how long that force has been acting on something, right? So that's why this incorporates that sort of the time factor or the time duration in which a force is acting on an object. And yes, so this property is known as impulse essentially. इसके बारे में I don't think I have much more to say than that. So this one as well, it's just a function of the vector f, so it acts in the direction of f, and because it's a force integrated with respect to time, it has units of Newton times second. Okay, अब इसकी एक example के तौर पे ना what's useful is, because again it's an integral of f with respect to time, so what's useful is always to plot the force against the time. Then this integral is going to be the area under the curve, right? Area under the force time curve. So अब एक golf की example लेते हैं. So what happens is कि when you strike the ball with your club, it's going to be in contact with the ball for a little while, right? So during this contact, it's going to transfer this sort of this impulse into the ball, जिसकी वजह से from this expression that we've just derived, there's going to be a change in the momentum of the ball. Okay. Right. So any questions so far? Not yet. Okay. So this expression that we've been talking about is known as the principle of linear impulse and momentum. Linear being important here because we are talking about a particular type of motion so far. And what it does is, जिस तरह हमारे पास principle of work and energy था, this essentially relates the particle's initial and final momentum to how much impulse was provided by the force which was acting on it. Okay, so overall it's relating the force with the velocity of the particle and the time over which the force acts. So it relates force, time and velocity. Okay, so nothing too complicated. Let's just write it down using the symbols that we had just introduced. So impulse represented using I. So going from T1 to T2, then it's just the summation, right? There's a summation there. The total impulses which act on the object, so I1 to 2, will be equal to the change in momentum of the change in linear momentum of the object or the particle. Okay, so yes, अब हमने इसको जब इस sort of convention में लिख दिया है, then I think this is looking pretty similar to something else. What does it look like? Any guesses? Have we seen a similar expression like this before? But instead उसमें impulse और momentum नहीं था बल्कि कुछ और था.
Principle of work and energy.
Exactly, thank you very much. So this is exactly like the principle of work and energy, or the method was also exactly the same, which was we were taking the equation of motion and implementing a kinematic relationship into it. Just instead, there are a few differences. So let's just talk about the similarities, right? So clearly what's happening here is that whatever for the principle of linear impulse and momentum, whatever impulses are acting on the object, the sum of them leads to a change in the momentum. Whereas for the work and energy, it was all of the work being done on the particle leads to a change in the kinetic energy. So even just to मैं बोल रही हूँ, that sounds so similar, right? Further, let me just point out a few more things. कि जो the quantities, the physical quantities on the left hand side, so this is the impulse and this is the work done, they are both associated with the external forces that are acting on an object. तो उस external force की वजह से क्या impulse है या उस external force की वजह से क्या work done हो रहा था. So these two are, if you think about it, वो उस force की वजह से क्या process हो रहा है उस particle के ऊपर. Whereas on the right hand side, we have some change going from an initial to the final state of a particle in one physical quantity. Here it's the momentum, whereas here it was the kinetic energy. So the right hand sides are associated with the initial and final states of the particle. Okay, so the left hand side is some sort of a process by virtue of the force acting on the particle, whereas the right hand side is just associated with the पहली state क्या थी और फिर बाद में क्या हो जाएगी इस process के बाद. Okay, लेकिन इसमें there are even though they look similar, there are some very key differences that we must be really careful about. Please notice that all of these symbols, not all, sorry, I and L are boldface. whereas here they're just non-bold face. Why? Because these quantities in the principle of impulse and momentum are all vectors, whereas in the principle of work and energy they were scalar quantities. Okay, so be careful about this. This is a vector equation. So as we'll see shortly, a vector equation implies that it's going to have 3 scalar equations within it. We'll just discuss that in a short while. There's another side note that I want to discuss, which is that let me manipulate this in a little different way, which is to go backwards, which is again to write down that I know that the impulses are actually the integrals of the force over with respect to the time on which they're acting. So either तो I then end up with an integral of with respect to time. So if I manipulate this further, right? मतलब ये कि मैं पता है मैं क्या करती हूँ, मैं actually इसका differential ले लेती हूँ उस पूरी equation का. Then what would I get? I'd get my summation f on the left hand side as it is, whereas on the right hand side I'd actually be getting the integral of L2 minus L1 with respect to time. Right? और ये the differential of L2 minus L1 itself is actually just the differential of the momentum with respect to time. Right? मतलब ये कि इसी चीज़ को वही मतलब मैं जो पहले चीज़ फॉरवर्ड जा रही थी अभी उसी को मैं बैकवर्ड लेके जा रही हूँ, just to point out one thing, that actually the resultant force that is acting on a particle can also be sort of described or defined or spoken of in terms of the change in momentum of the particle. And if we look more closely, then the resultant force that's acting on a particle at a given time is actually equal to the rate of change of its momentum. Now, I think this would be pretty self-explanatory for most of you because we know that summation f is equals to ma, right? So agar A I know is mdv by dt, so I can just take the mass inside as well and then it just becomes, right, which is dl by dt. I'm pretty sure मैंने इधर एक इस step के अंदर एक गलती की है, लेकिन just थोड़ा simple करने के लिए अभी मुझे करने दें ये. My point just is that the resultant force, when we talk about it in terms of the accelerations, can actually also be considered in terms of the rate of change of its momentum of the particle. Okay, so that's also something which is a little important to keep in mind. Okay, वो force की वजह से a change in momentum is caused for that for a particle. This is actually just another way of stating Newton's second law of motion, but it is basically Newton's second law of motion. Okay, right, so coming back to our principle of impulse and momentum, I've just rearranged it ताकि वो जो the term that I had on the right hand side, I've just brought it to the left hand side ताकि इसको भी हम उसी form में state करना शुरू कर दें as we had been stating the principle of work and energy, which is that the final linear momentum of a particle is given by the initial momentum of the particle plus the sum of all the impulses acting on it. So pretty straightforward and similar sort of definition of what we've considered previously. Okay, so I'm.
मैम एक
हाँ जी please.
मैम ये लीनियर इंपल्स जो हम कह रहे हैं तो पार्टिकल हमारा स्ट्रेट लाइन में मूव कर रहा है कि वो कर्व में भी हो सकता है, कर्विलिनियर भी हो सकती है मोशन?
वो कर्विलिनियर भी हो सकता है.
तो लीनियर से क्या मुराद है कि रोटेट नहीं कर रही बॉडी?
नहीं, लीनियर से और कोई मुराद नहीं है एक्सेप्ट कि हम उस पार्टिकल का मोशन उसी के टर्म्स में कंसिडर कर रहे हैं, not with respect to some other origin or something else. Okay, that wasn't too clear. मतलब ये कि let's consider I have a particle right here which was initially going in this direction. रुके मुझे अभी डायग्राम बल्कि बनाने दे, मैं अभी आपको दिखाती हूँ इसके नीचे ही आ रही है. So let me just show you that. This one, ठीक है जी. So what's happening here a particle has an initial momentum which is going in this direction, mv1. अब बेशक वो ओरिजिनली किसी कर्विलिनियर उसमें जा रहा था, मुझे उससे कोई सॉर्ट ऑफ गर्ज नहीं है, राइट? वाई? बिकॉज मैंने इस पॉइंट से उसका सॉर्ट ऑफ अपना, अगर मैं चेंज मैं t1 से t2 जो ले रही हूँ, डज दैट मेक सेंस? सो आई हैव माई mv1 एक्टिंग लाइक सो, then of course उसके ऊपर there will be some forces acting on it which may be, जिसको आप उसके tangential और normal components में भी break down कर सकते हैं इधर से, right? So all we need to do to figure out कि उसकी final velocity या फिर उसका final momentum क्या होगा is to consider the impulses because of those forces. ठीक? Or in other words, if I have my curvilinear motion like so, then if I know कि वो इधर से initially यहाँ था and there is a F tangential and Fn acting on it, then using these two forces, if I just find their impulse, then मुझे उसके अगले point की ही direction momentum पता होगा. Does that make sense?
Yes, ma'am.
Okay. So previously अगर हमें यही चीज़ यूज़ करनी थी कि हम कर्विलिनियर पे एक पॉइंट से अगले पॉइंट पर डिटरमिन करें कि उसके ऊपर गिवन ये फोर्सेस एक्ट कर रहे हैं, then what we would have had to do is कि पहले we would have had to apply our Ft is equals to mat, our equations of motion, right? और उसके बाद हमें इनसे हमारी एक्सेलरेशंस पता चलती, जिन एक्सेलरेशंस को यूज़ करके हम फिर उसकी वेलोसिटी निकाल सकते होते, और वेलोसिटी का रेट ऑफ चेंज भी, जो भी करना था हमें, राइट? सो द पॉइंट इज इधर देयर इज वन स्टेप एंड द सेकंड स्टेप इन्वॉल्व्ड. Whereas if we just directly use our principle of impulse and momentum, फिर हम directly forces को उसकी velocities से ही relate कर सकते हैं. That's what I'm trying to get to. ठीक है जी. So it does not, the linear is not related to the type, it's general motion जिसके ऊपर linear आता है. वो जो angular motion momentum है ना, हम उसको we will talk about it later on. Just for now think कि आपको पता भी नहीं है कि angular momentum कोई चीज़ होती है. All that you know is that there's the momentum of an object, or it's called the linear momentum, and that's just given by m times its velocity. Velocity जिस मर्जी direction में भी हो, जिस मर्जी उसकी path भी हो, does not matter. ठीक है जी.
मैम अगर वेलोसिटी गिवन है तो हम टेंजेंट कंपोनेंट लेंगे उसका, बस वेलोसिटी का.
ये किसने पूछा है?
किसी ने नहीं.
ये नाम ही नहीं ले रहे. नहीं, ये डरे नहीं, ऐसी बात नहीं है. मैं सिर्फ आपको थोड़ी डांट लगाने के लिए इसलिए नाम पूछ रही थी. नहीं, आई एम जस्ट जोकिंग. वेलोसिटी हमेशा टेंजेंशियल होती है. रिमेंबर, वेलोसिटी इज ऑलवेज टेंजेंशियल टू द पाथ. वेलोसिटी हमेशा टेंजेंशियल होती है. वेलोसिटी का कोई नॉर्मल कंपोनेंट होता ही नहीं है. इसीलिए मैंने उसको vt ही लिखा था, बिकॉज इट्स जस्ट वेलोसिटी का है ही यही कंपोनेंट इन द एंटी कोऑर्डिनेट्स. जिसने पूछा था वो गायब कहाँ हो गए? ये तो एक्नॉलेज तो करें कि ओ यस, मुझे याद आ गई ये बात.
यस मैम.
ठीक है जी. अगर आपको अनक्लियर है कि ऐसा क्यों होता है, तो पहले तो आप अपने किसी दोस्त से पूछेंगे. फिर अगर आपको तब भी अनक्लियर होगा, फिर यू विल आस्क मी कि मैम ये वेलोसिटी क्यों ऐसे, व्हाई इज इट ऑलवेज टेंजेंशियल? ओके. ठीक है जी, चले. थैंक यू वेरी मच. ओके, सो इधर लेट्स कम बैक टू दिस. सो इसी प्रिंसिपल ऑफ इम्पल्स एंड मोमेंटम को लेट मी जस्ट शो इट इन डायग्रामेटिक फॉर्म, right? Which is कि if I have my initial momentum इसका मतलब ये कि mass multiplied by the velocity, so mass multiplied by a vector. So it's just going to be representing a vector, which is the initial linear momentum in the direction of velocity. And then add on top of it all the impulses which are acting on the particle. So then that's called the impulse diagram. और अभी मैंने इधर ना just the summation ही draw कर दी, whereas what we can do is कि वो जो individual forces act कर रही हैं उन सब का आप जो the vector which is the impulse को draw कर लें, and then you can use the head to tail rule, या फिर you can just use arithmetic by resolving them in components to add them up. ठीक है, we'll discuss that. And then that gives us of course the final momentum. ठीक, so please notice कि this is going to be a vector, and then there is a मतलब impulses का summation का vector, that is the resultant impulse का vector, and then the summation of these two, just add these two vectors together and that will give us our final momentum. So because the reason why I'm pointing this out is कि इस सब कुछ के ऊपर वही vector methodology apply हो सकती है. So head to tail rule and so on can be applied on it if we want to go via the graphical or diagrammatic route. ठीक है जी. So just to point out here कि जिस पे momentum हम show करें, that's known as the momentum diagram, whereas the one which is showing either each of the individual impulses or the total impulse on the particle is known as the impulse diagram. Okay, so it can be helpful to draw these out जिस तरह हम free body diagram बनाते हैं ताकि हमें थोड़ा सा picture मिल जाए of what's happening. Okay, and then of course या तो आप diagrammatic route से जाएं या फिर my personal preference is to just use scalar versions of equations ताकि vectors को आप add and subtract कर सकें. तो फिर that basically means कि जो ये हमारी vector equation थी, this one right here, what I can do is कि ये initial momentum को I can find its components in the xyz direction, या तो and then for the total impulse उसके भी I can find the components in the xy direction, and then finally for the final momentum ताकि I can manipulate them just by straightforward addition. ठीक है जी, straightforward ये अब scalar versions बन गए. ठीक है जी. So of course it's just the same principle in the x direction, in the y direction, in the z direction. So nothing fancy happening here. So I'd recommend to you guys कि जिस तरह हम free body diagram बना के हर चीज़ को फिर vectors को analysis उसके individual components में कर रहे होते हैं, तो इधर भी ऐसे ही हमें करना चाहिए. Now let's come to it कि let's solve a few problems. Secondly, मैंने इस दफ़ा applications बाद में move कर दी थी just to change things up a little bit. So what's happening with all of this principle of linear impulse and momentum is that our initial momentum plus the sum of all of the impulses acting on the object is going to be equal to its final momentum. ठीक है, so यही there is this principle which is used whenever we're talking about actually किसी भी चीज़ का motion के ऊपर. ठीक, so as just an example, there is a rocket, ठीक है जी, जिसकी पीछे से there are exhaust gases which are released at a very high pressure, मतलब बड़ी तेज़ी से वो निकलती हैं, right? So I'm starting to talk about these time factors, right? So if those gases escape really quickly, then what happens is that there's a very large impulse which is generated by them on the rocket. That's number one. Number two, also कि उनकी वजह से there's a momentum which is being generated in the sort of the backward direction, which provides the rocket's forward momentum essentially. ठीक है, और इस aspect जो मैंने अभी कहा है कि एक इनकी तरफ से momentum होता है और एक उसका momentum होता है, वो हम ज़रा बाद में बात करेंगे. Just as we had discussed, there was a conservation of energy. There's also something which is the conservation of momentum. We'll talk about that later on. But the point is, just for what we know, this is allowing us to determine कि किसी object of interest to us, how do we determine कि उसका जो भी हमें final momentum required है, that is एक ship को हम चाहते हैं कि वो आगे forward direction में propel कर रही हो at a particular velocity, then what impulse do we require? मतलब ये कि उस पर किस किस्म की thrust force act करनी चाहिए, for how long? Okay. So as I said before, again it's still things which we can analyze using our, and A is equals to dV by ds, dV by dt, or A ds by dV dV, or so on. So just one step and two step, or directly using the principle of impulse and momentum. ठीक है, तो मतलब it's not really new, but it provides us a direct way of relating them. So either be again it's a problem कि whenever we're sort of, let's say, smacking a nail into some piece of wood or the wall or anything, then that hammer से हम एक impulse provide कर रहे हैं. There's a force that acts on the nail for a very short duration of time, और वो very उस short duration के अंदर एक impulse transfer कर रहा होता है into the nail, जिसकी वजह से there's an increase in the momentum of the nail, और वो it gets driven in to the wood or whatever it might be. Okay, that is using directly the principle of linear impulse and momentum, we can relate कि क्या force कितने time पे act की थी और उसकी वजह से क्या velocity होगी of our object. Okay, of course don't forget m भी है वहाँ पे, so there's mv, it's the momentum which is changing. Perfect. So let's with that, let's jump into some examples. As always, our methodology is going to start with the same old घिसे पिटे तरीका, which is कि हमेशा 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 हमने अपने inertial coordinate system को set up करना होता है. Most probably in our case here we will be using our Cartesian coordinate system, although we can use the other ones as well. There's nothing stopping us doing that. And then we'll draw our, either आप free body diagram भी हम बना सकते हैं, या फिर we can directly draw our what was it, momentum and impulse diagrams. Just हमेशा diagram बनाने से एक visual understanding मिल जाती है of the problem. Then we write down the scalar versions of the principle of linear impulse and momentum, and then solve it. That's it. Pretty straightforward. Last thing that I just want to point out is that the principle did involve an integral of force with respect to time. Okay, so that force needs to be integrated with respect to time. Only जब it's a constant force, then of course हमारी वो integral becomes, if it's a constant force, then we have the force against time is just this, right? So then it's a straightforward area under the curve is just force times whatever delta t it was, right? The area of a rectangle. Hence why in that case it's a bit more simpler, the impulse applied or supplied by this force. Okay, so let's see this. Let's see an example for it. Please get your pens and papers out. Okay, so आज तो मैं नोट करी थी पिछले 2-3 क्लासेस से मैं ही सॉल्व कर रही हूँ. Not fair. So this example you guys are going to do first, and then I'm going to start to pick up the pace, or I want pictures from you lot in the chat, okay? So there's a golf ball which is hit over a time interval of 3 milliseconds by a driver. The ball leaves with a velocity of 35 meters per second at an angle of 40 degrees. Okay, what do we want to do? We want to find the average impulsive force exerted on the ball. Perfect. What's happening? So we know the time interval, we know it's sort of the velocity, and we want to find the force. So clearly it's the principle of impulse and momentum that we need to apply. And then after that we want to find the momentum of the ball 1 second after it leaves the club. Okay. Okay, so please start.
मैम एवरेज इम्पल्सिव फोर्स से मुराद फोर्स ही है ना यहाँ पे?
आपको क्या मतलब एवरेज क्यों लिखा होगा?
मैम लेकिन वो मतलब फोर्स तो एक ही लग रही है ना, ये अपने ये जो उसका गोल्फ की जो होती है रॉड जो
बिल्कुल ठीक। अच्छा
उससे।
देखें, बात ये है कि आपको तो नहीं पता ना कि वो फोर्स किस तरह है एज अ फंक्शन ऑफ टाइम। दैट इज़, जिस तरह मैंने पहले कर्व दिखाया था, व्हाट्स पॉसिबल इज़ कि वो जो गोल्फ क्लब का, क्लब से मैं सी रिप्रेजेंट कर देती हूँ, क्लब की जो फोर्स है ना अगेंस्ट टाइम, मोस्ट ऑफ द टाइम इट्स एक्चुअली समथिंग लाइक दिस। इट्स एक्चुअली अ फंक्शन ऑफ टाइम। जैसे वो कांटेक्ट में आता है तब वो लो होती है, फिर वो आहिस्ता 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 हाई पे पहुंच के फिर जब फाइनली कांटेक्ट ख़त्म हो जाता है। ठीक है, तो ऑल ऑफ दिस वुड बी द इम्पल्स प्रोवाइडेड बाय दिस फोर्स। तो हम एवरेज इसलिए कह रहे हैं क्योंकि भाई ये तो एक फंक्शन ऑफ टाइम है। इंस्टेड इसकी जगह व्हाट वी कैन फाइंड इज कि व्हाट इज़ व्हाट इज़ द एवरेज फोर्स जो इसी के जितना इम्पल्स प्रोवाइड करती है। मतलब ये कि अगर इसी इम्पल्स को हमने एक कांस्टेंट फोर्स से प्रोवाइड करना होता, इस एवरेज फोर्स से, तो देन व्हाट वुड बी दिस फोर्स विच हैज़ द सेम इम्पल्स एज दिस function of force which is a function of time. Does that make sense?
यस मैम सही है।
थोड़ा थोड़ा Okay, so I think I've given you a good head start. I'll start now and I'll keep quiet so I don't disturb you guys. Anyone who's already found the impulsive force, where are you guys? हैं आप लोग गायब कहाँ जाते हैं?
मैम आंसर बता देंगे।
मैं खुद नहीं पहुंची अभी तक वहाँ। एक सेकंड, तो मैं आपको इधर करूँ। सब मैं ज़रा जल्दी करूँगा, शर्जील ने कर भी लिया। ओके, इम्पल्स dt और 0 से 3 milliseconds, and this is going to be equal to 35 m. Okay. ये तो मुझे गलत लग रहा है मेरा, लेकिन बहरहाल आई एम गेटिंग 467 न्यूटन्स, which is at 40 degrees away from the horizontal. Sharjeel, is that what you're getting? Anyone?
Yes.
शर्जील बोल लो।
Yes, ma'am.
अच्छा जी, 2-3 लोगों ने कंफर्म कर लिया, तो फिर आई एम गना
यही निकला।
यही आया। ओके जी, सो इम्पल्सिव फोर्स तो आ गई एटलीस्ट। डोंट फॉरगेट दिस इज ए वेक्टर, सो इट्स 467 न्यूटन्स इन द 40 degrees direction. Anyone who has not been able to solve this so far? कोई भी नहीं? नहीं? अच्छा, just to point out कि इसमें I have made some assumption. कोई anybody would like to discuss that with me or not?
मैम उसने वैसे ये नहीं पूछा हमसे कि हमने एवरेज इंपल्सिव फोर्स और मोमेंटम 1 सेकंड आफ्टर इट लीव्स द क्लब फेस बताना है, तो ये होगा इनिशियल इसका, तो वो स्टार्टिंग पोजीशन पे नहीं होगा इतना इंपल्स,
ये तो
क्योंकि अगर 1
ये तो स्टार्टिंग पोजीशन पे ही है, ये तो फोर्स उसके बाद लग ही नहीं रही ना, so it only acts for these 3 milliseconds and then after that it's gone,
सही,
right? So it's as if this 3 milliseconds is representing the point of contact, the point at which we're hitting it, right? तो उसके बाद अभी अगले पार्ट पे तो मैं पहुंची नहीं हूँ कि मोमेंटम आफ्टर 1 second, so the force acts only for 3 milliseconds. After that the force is no longer acting on it. So let me just go over कि इसी वजह से I have made certain assumptions, because I'm assuming कि force is acting for such a short time, during which what I'm doing essentially कि अगर if you guys notice कि जाहिर है there are going to be other forces acting on the ball as well, which include its weight and the normal force, right? There's going to be a weight acting on it and the normal force exerted by the pin right here. But what I'm going to do is I'm just assuming कि ये फोर्स बहुत सडनली एकदम से आके अप्लाई होती है, राइट? सो ओनली फॉर दिस वेरी शॉर्ट ड्यूरेशन पहले से हमारे पास जो वेट और नॉर्मल फोर्स थी वो तो इक्वल बैठी हुई थी ना, जब वो यूं करके एक दूसरे के, बिकॉज इट वाज इन अंडर एक्विलिब्रियम. सो आई एम जस्ट, दिस इज अ मैसिव assumption, but I am gonna assume कि either I can say it this way, which is कि right before the action of the force these two are equal, such that इनकी वजह से the impulses they cancel out both of these. But the
मैम बॉडी रेस्ट पे तो वेट या नॉर्मल फोर्स की वजह से तो मोमेंटम वैसे ही नहीं हो सकता।
वही तो बात है, यही मैं आपको कहना चाह रही हूँ कि immediately before the action of this force these two would have been equal. लेकिन आफ्टर दैट तो जाहिर है वी आर अनेबल टू फाइंड के वो नॉर्मल फोर्स क्या होगी, क्योंकि वो तो चेंज हो जाएगी ना, राइट? इट डजंट नेसेसरली नीड टू बी equal to the weight. but what I'm saying is कि immediately before that it was equal, and I'm just going to carry on assuming कि वो जो 3 milliseconds है ना, उसके दौरान भी वो normal force इतनी rapidly change नहीं होती, and such that instead what ends up happening is कि the impulse during that short 3 millisecond interval of the weight and the normal force cancels out. That's one way of saying it. The other way is also to think about what the magnitudes of each of these forces and their impulses is going to be. Look at its weight. It's so small, or because of that, the impulse caused by this weight और फिर वही जो normal force पहले से exist कर रही थी, those impulses are going to be pretty small. अभी मैं I'd like you to calculate the weight. मैंने directly नहीं लिखा था, मैंने सिर्फ weight is 40 exponential minus 3 into 9.81. The weight is 0.39 newtons. Compare this to the average force जो हमने निकाल लिया है. This is tiny. So the impulse caused by the weight and the normal force are going to be so small that they can just be ignored. They're just negligible. Okay? So that's why I had ignored, वैसे भी question में लिखा हुआ है neglect the ball's weight while it struck. But even if that was not provided to me, I would have made this assumption because the impulses because of these two weight and the normal force are not, they're going to be negligible. Okay? Right. So is this clear to everybody?
Yes, ma'am.
Excellent. Okay, now comes the momentum of the ball 1 second after it leaves the club face. What's happening is कि हमें अब momentum निकालने के लिए 1 second afterwards. Then what's happening is कि as it goes off 35 पे at 40 degrees. Now, after it's been struck, it's a case of projectile motion. Right? So what I can do momentum निकालने के लिए, I'm actually going to use kinematics. I know that my momentum is mv, right? So if I just find the velocity that this ball will have after 1 second and multiply it by the mass, I'll know what the momentum is. So let me define my x and y's. The first सीधे define कर लेते हैं. And I know as part of my projectile motion that the horizontal component remains unchanged because there is no acceleration in the x direction, right? So that just means it's 35 cos 40. Whereas for the vertical component, I know that that's a case of constant acceleration because of gravity, नीचे की तरफ. So that's going to be 35 sine 40, पहले तो upwards था, and then there's a minus 9.81 times how much? After 1 second निकाल देना, so 1 second. Please note this is just my, वो जो हमारी होती थी ना V2y is equals to V1y minus gt, right? Projectile motion, in which I have a case of constant acceleration for the vertical component of velocity. So that's it. This gives me my x and y component, and if I multiply these two, I will find my final momentum, let's say, let's call it, or that's going to be 0.04 multiplied by each of these. So I'm gonna leave it for you guys to calculate, so I can just write it as vxi or minus या plus, I don't know what it would be. I'm going to leave it as vyj, or where vx is this one, vy is this one, and m is its mass. So pretty straightforward, right? Okay. Now note के इस किस्म की problem को प्रिंसिपल ऑफ इम्पल्स एंड मोमेंटम, प्रिंसिपल ऑफ इम्पल्स, हाँ जी
सॉरी मैम, हमारा 1 मिनट में क्विज शुरू होने लगा इलेक्ट्रिकल का, तो मैम अगर आप इजाजत दें तो जाना पड़ेगा हमें.
ओ ऑफ कोर्स, सबका